Hello guys. Uh, so this is the new topic, that is structural dynamics, and this is related to the structural dynamics as well as earthquake engineering. So in very statics, we are going to deal with the degree of freedom. So degree of freedom, starting from the very basic definition. Okay, so degree of freedom is total number of independent coordinates displacements on a structure. Okay, in a generalized structure, it means that the number of independent displacement that is happened to a structure when some force is applied. Okay, that is independent displacement that structure can possess. Okay, let me clear you the degree of freedom by using a simple example. That is a framed structure. So one is here, you are seeing one is here the not rigid frame, and one is the rigid frame. So one is the rigid frame and another one is the non-rigid and rigid frame. So rigid beam cancel out the displacements, okay, at the intersection points. Okay, now considering the displacement, this will be the displacement for the not rigid beam. 1 2, here it is 1 2 and 3. So we can say that 3 degree of freedom. So in a rigid frame there is only one. So in rigid frame there is only single degree of freedom. You can say that single degree of freedom. To represent a single degree of freedom, there is a concept of simple harmonic motion occur. So why we need simple harmonic motion in a structural dynamics? Okay. Uh, so simple harmonic motion. Okay. So in simple harmonic motion of a rigid frame. Okay. So what will happen actually? I'm going to explain that. So simple harmonic motion, you can say that stiffness, in that term we need to first understand the stiffness. So in stiffness, that means the ability of structure to resist deformation due to the applied force. Suppose we have a rigid frame having this mass m. Okay, so we know that here the degree of freedom is 1. Okay, so it possesses some, stiffness. We can denote that by the k. Okay, so if we damped that, okay, so we have some damped structure इस तरीके से. Okay, so it can be denoted by the c. So let me represent this by a simple mass system, considering the structure. Let us suppose this is mass m, which is placed over a smooth surface. So this is the roller actually placed over a smooth surface. Wait. So due to its mass, it possesses some stiffness, which is represented by stiffness K, and there is a damping coefficient, that is C. So we are also applying that C, and it is subjected to a force P, that is PT, time dependent force. So we can, so this is simple mass spring system. And remember that mass is only permitted along in the direction of the spring. So let us draw the simple free body diagram of this system. Okay, so the structure or mass M is subjected to a force PT. Okay, this is the mass M. Let just the direction of force applied is PT in this direction, And considering the structure free from the damping, that is C is equal to 0, the structural spring force is in the opposite force of the applied force. So K into the displacement, lattice displacement, you all know it is represented by BT. So external force is also studied by the Newton's second law, that is unbalanced force will be directly proportional to the acceleration, that is from the Newton second law, that is time dependent acceleration. This is the free body diagram. Free body diagram. So if the mass is m, if the mass is m subjected to a force Pt with the spring system K, then what will happen? Okay, so it will equals to this kV into T, which is equals to the Pt. That is the simple concept. And here Vt is what? It is initial displacement of the structure. Okay. Now, any unbalanced force is directly proportional to acceleration. That is from the Newton second law. Okay. So, we can say that K into Vt minus Pt is equals to the m into, that is the mass into acceleration, that is m u into t. Okay. Uh, and then I said any unbalanced force is balanced by the acceleration from, so this kV into t minus pt is equals to mu t. So we can further modify this, that is pt is equal to mu t plus kVt. This is the simple harmonic, this equation is simple harmonic motion equation, which is equals to the mass into acceleration k into vt, spring constant into displacement, which is equals to the force that changes with the time. This is the simple harmonic motion of a single degree of freedom, you can see. There are some now key terms which you are need to understand. Okay, so some key terms. So we have the from simple harmonic motion, we know the equation is equals to this, that is pt is equal to mu t plus kv t. Now for the free, okay, so now for the vibration that is of free from any other force, we can say that is the free vibration. So here no force, then how the vibration main concept is arise when we call the free vibration. So if the no force is applied, how that vibration comes, that question must be arise in our mind. So initial displacement sets in the vibration. Okay, so due to the initial vibration we have the this concept arises. Okay, so here the force, no force means this Pt leads to 0. So the modified simple harmonic motion is equals to the 0, which is equal to mut plus kv into t. Okay. Now for the free vibration, that is no external force applied. So we have this u is equal to mut plus kv into t. Okay. Now, to get the further modification of this equation, uh, we divide the equation number 1 by the mass. So, divide equation 1 with mass m. Okay, so you can say that u into t is equals to the k by m v into t, which is equals to 0. Now this k upon m is equals to the omega square. Okay, and this omega is equals to the k by m under the root. Okay, now omega is equals to what? Omega is equals to the angular frequency of vibration, angular frequency of the vibration motion. You can see. So in equation this number 2, you have this u into t plus this okay, k by m is equal to the omega square v into t, which is equals to the 0. Okay, and from here u into t, which is equals to the minus omega square into v into t. V into e is equals to the displacement. Okay. Mm. Now the concept arises, that is the type of the loading. From the given equation, we are also describe the type of the loading. So we have the two types of vibration. That is, one is free vibration, another one is the forced vibration. So in free vibration, there is further divided into two. That is, one is damped and second one is undamped vibration. And in the forced vibration, there is also two. One is damped and another one is the undamped. Okay, so what will happen in the undamped free vibration and damped free vibration? So very first is your free vibration. So free vibration, undamped. The equation, so equation for this undamped free vibration, time dependent graph, that is applied forces remain constant, that oscillation is also remains constant. But for the damped free vibration, damped free vibration, oscillation decay exponentially. Okay, so how the equations of simple harmonic motion changes according to the forced or in the free vibration. So in the free vibration, so in the free vibration, the force, no force is applied. So in undamped, C also equals to 0. In damped, there is some value of C. In undamped, C is equal to 0. Or here the value of C is also there. So in free vibration undamped, you can say that M U plus KB, which is equals to 0. Free vibration, and mu plus KB is equals to PT. That is the forced vibration. And in damped, there is a C also there accompanied. This equation is accompanied by the C. Okay, so in damped, we have this equation further modified to M into U plus C into G, which is equals to the PT. Okay, also KV is also there. Okay, this is the free, this is forced damp, forced damp equation of simple harmonic motion, and kv plus mu plus c into v, which is equals to the 0. This is free damp equation of simple harmonic motion. So that's all for today. Thank you.